Kia ora koutou, no mai, haere mai. Welcome to lesson 2 for introductory physics. This lesson is going to look at measurements, units, scientific notation, and uncertainty. So quite a bit to get through. The reason I've put these all together into one lesson is that it is essentially all the information you need to go and start doing the lab reports, the lab work that is assigned for this course. I only called it measurements and uncertainty because it was a bit long to put all four in the title. But there are those four separate sections that we're going to cover. So as usual, we'll jump over and look through the slideshow. Starting off, we are looking at experimental science in general. So this is the concept of measuring something. Quantitative means dealing with numbers and equations. So if you think of the word quantity, quantitative, it's talking about quantity, it's talking about numbers, about values. So when we're talking about experiments, we are often talking about quantitative data, quantitative being numbers and values. So if you're going to do quantitative analysis of an ice cream, you might consider its mass, its density, its calories, its sugar content, its fat content, and so on. That is quantitative information, anything that you can assign values and numerical data to. The other side of that coin is qualitative data. So qualitative, qualitative, it's talking about the quality of something, it's descriptions and ideas. So you might undertake qualitative analysis of an ice cream by interviewing taste testers, by gathering descriptions of flavors and brands and tastes and things like that. So qualitative is descriptive, quantitative is numerical data about something. Physics is a bit of both, as is any science, right? Any science is a bit of both. Much of what we do is quantitative because we're going to go and measure something. We're going to do some calculations. We're going to derive formulas. We're going to use maths to develop models that apply to the real world, and then we're going to get quantitative descriptions of different phenomena. That is quantitative study, and it is a lot of what we do, but none of it makes any sense without the qualitative understanding of what's actually going on. So you need to have some description, some idea of what's going on in order for the quantitative stuff to actually make any sense. So there is a bit of both. That said, the experimental physics, the measurements that we're doing, that's all quantitative. So when we take a measurement, which is how we conduct experiments, it's how we do experimental science, you might just grab something and you might want to know the length of it. So you might get an object, you might get a ruler, and you might measure the length. That is called a direct measurement because you used a tool to obtain the value that you wanted. That's it. You directly got the value you wanted from the object using a tool. However, sometimes you want to know something that you don't have a tool for. So you might want to measure the volume of a brick, and all you've got is a ruler. So you measure the length, the width, and the height of the brick, and by multiplying them all together, that's how you get a volume of a rectangular prism. I hope you're all familiar with that concept. Look up volumes if you're not sure. Volume of a rectangular prism is just length times width times height, and that tells us the volume of the brick that we have measured. That is an indirect measurement. Indirect because we didn't have a tool that could directly tell us. That's all indirect means. There's no preference between the two. One isn't better than the other, but which one we use is going to be determined by which tool we have. If you have the option to take a direct measurement, you might sometimes think that that's better, and sometimes it is, but there are actually instances where the tool you have to get your direct measurement is not as reliable or not as precise, and so you end up preferring to do an indirect measurement. So there's no actual preference. The preference is around the tools and our confidence in them. And as we'll see when we do some experimental work, and in the very end of this lesson, we have uncertainties, and so trying to improve our precision is also a relevant factor. You will, of course, undertake both forms of measurement, indirect and direct, during the labs for this course. Units and unit conversions is the second thing that we're going to cover. So what is a unit? Well, if I ask you what the mass of a litre of water is, or if you ask me, as I've written on the slide, and I just say 1, am I correct? If I don't give you a unit, then it's essentially meaningless. It is meaningless if I don't tell you the units. 1 litre of water has a mass of 1 kilogram. That's actually how the litre is defined. It's 1 kilogram of water, which is, as we know, 1,000 grams. 1 kilogram is 1,000 grams. So if I just say 1, that doesn't mean anything. But if I tell you a litre of water has a mass of 1 kilogram, then that's correct and that's useful information. So we need units to make sense of our quantitative data in most cases. There are some times where it doesn't matter. If I ask you how many pens I'm holding up and you say 2, that's correct. You don't need units. There's no units for just a count if you just count something. So there are units for most values, but occasionally you'll see something without a unit. Which units do we use? In order to communicate scientific results with other people, we want to tell them our results in some unit that they're going to understand. I could go and tell you how many cars my elephant weighs, right? I could weigh it. I don't have an elephant. If I did, I could weigh it. I could compare it to my car and see how many cars my elephant weighs, or vice versa. But that's not useful for anyone else because they don't have access to the mass of my car or my elephant to compare them. So what we do instead is we have SI units. We have agreed upon units that everyone just says, right, these are what we're going to use. So for density, density is expressed as kilograms per cubic meter. You may not be familiar with density yet. We will introduce it. I'm just using it as an example for now, so don't worry too much if you haven't met it before. But density is kilograms per cubic meter. You could use any unit for mass. You don't have to use kilogram. You could use gram. You could use ton. You could use any unit for mass. And you don't have to use cubic meter. You could use any unit for volume. You could use cubic inch. You could use litre. You could use milliliter. You could use whatever you want. So I could tell you density in tons per cubic inch, and that would technically be correct, but it's useless because people don't know what tons per cubic inch are offhand. It's not technically useless. You could go and convert it, but it introduces a whole lot of work to do that unit conversion. So it is always preferable to present our values in the units that we all agree, the scientific community agrees we will use, and that is what the SI units are. There are 7 fundamental SI units. They are listed here: the kilogram, the second, the meter, the Kelvin, the ampere, the mole, and the candela. We are not going to look at candela at all. We will meet mole very briefly, but we will use the other 5 significantly: kilogram, second, meter, Kelvin, and ampere. We will use all of those. There are other derived units. So when we have things like the Newton that we'll meet when we talk about forces, that is derived from these ones. It is equal to the kilogram times the meter divided by seconds squared. So they are derived units, but it comes back to these SI units. So the Newton is an SI unit, but these are the fundamental 7 SI units. As I said, if we get given a value in some other unit, like tons per cubic inch or something strange, we need to be able to convert it to something that we can use. So occasionally we will need to do these. We will often make you do them when we're doing exercises and problems and tests and things. In the real world, generally all you would need to do is convert from the value that your measuring device gives you to the value that you need to put into your calculation. But we try and overdo it with a bit of practice just to make sure you're familiar with them. There are several reasons for this. One is that in everyday life, we do deal with other units. For example, driving, we talk about kilometers per hour. That is not SI units because we've got kilometers instead of meters and we've got hours instead of seconds. So we still have a distance over a time for a speed, but we have non-SI units. So we need to be able to convert from kilometers per hour to meters per second in order to do any scientific analysis on those values. There is one really simple rule for unit conversion, and that is that if you multiply anything by 1, its value is unchanged. Hopefully you're all familiar with this. That's a very basic principle of mathematics. Anything times 1 is just equal to the original anything you had. It doesn't change the actual value. But what we can use that for is changing units. So if you know that 1 meter and 100 centimeters are exactly the same length, which is what they are, that's how they're defined, 100 centimeters in 1 meter, then you can take a value and you can multiply it by 1 meter over 100 centimeters, and that's just the same as multiplying it by 1. It will change how the number looks, but it won't change the actual value. It won't change the length. So the example here, 10 centimeters, we want to convert that into meters. So we're going to multiply by 1 meter over 100 centimeters. So that whole bracket is just equal to 1. So all we're doing is multiplying our length by 1. So we're not changing the length at all. What we are doing though is we're cancelling those centimetres, because we've got centimetres on the top from our 10 centimetres and centimetres on the bottom from our 100 centimetres. So we cancel out the centimetres. That leaves us just with the metres. And so then we have 10 times 1 divided by 100, or just 10 divided by 100, which is 0.1 of a metre. So you get 0.1 of a metre is equal to 10 centimetres. Hopefully that's not too much of a surprise. You're probably quite familiar with metres and centimetres, but all unit conversion is just this process. That's all it is. As you get better at it, as you get more practiced, you might not need to write this down in full every time as I've done here, but certainly if you're new to unit conversions, or if you're still not 100% confident in them, do this every time. Write down that bracket, write down all your units, cross out the ones that are being cancelled out, do the whole process in full, and hopefully everything will make sense. So anything multiplied by 1 does not change the value. As an example, you're driving in a car at 53 kilometers an hour. Let's convert that to meters per second. This is quite a common one, as I said. It's an everyday unit that we do use, and we often need to convert into meters per second. So this is one you'll get asked to do a lot. So how do we do this? Maybe I'll jump over and I'll do this on the document camera, just so that it's how you would see it as well. So we've got 53 kilometers per hour, and we want to convert it into meters per second. So remembering that all we can do is multiply by 1. Let's think about the fractions we have that are equal to 1 that are going to be useful for us. Well, we want kilometers into meters. So we have 1 kilometer over 1,000 meters. All right, 1 kilometer is equal to 1,000 meters. So this whole thing is equal to 1, which is good. We can use that. And then we've got hours and we've got seconds. Now, hours and seconds, you might not be very familiar with the conversion directly from one to the other, but hopefully you remember that there are 60 seconds makes up 1 minute, and 1 minute makes up, I should put min, not m, 1 minute makes up, 60 minutes makes up 1 hour. So if you've got 60 seconds in every minute and 60 minutes in every hour, then you have 60 times 60 seconds to make 1 hour. And that is equal to 3,600 seconds for 1 hour. So that means that another fraction that we can use is 1 hour. I've moved between H and HR, but 1 hour over 3,600 seconds. That is equal to 1 as well. They are the same time length. So we now have a bracket that will convert our kilometers into meters, and one that will convert our hours into seconds, so we can now do our unit conversion. So that's the first step of any unit conversion, is making sure you know these ratios, these fractions that will equal 1, that will convert from what you have to what you want. So let's take 53 kilometers per hour. I'll go back to HR just to be consistent. 53 kilometers per hour, and we're going to start by multiplying it by this bracket here, except that what we've got is we've got kilometers on the top here. If we want to cancel our kilometers, we're going to need kilometers on the bottom. So we're going to need 1 kilometer on the bottom and 1,000 meters on the top. Now we can cancel those kilometers. What we're left with is 53 times 1,000, so 53,000 meters per hour. So that's our value now after just doing that 1 conversion from kilometers into meters. Now we can multiply by this bracket. We've got hours on the bottom, this has hours on the top, so this one's already the right way up. So we just go 1 hour over 3,600 seconds. And that's going to cancel out our hours, and we're going to get 53,000, I'll move this page up slightly, 53,000 divided by 3,600, and we're going to be left with meters per second, which is what we want. So 53,000 divided by 3,600. You'll need a calculator for that one most likely, but it comes out to 14.72 meters per second. So that is how you do unit conversions. That's all there is to it. Figure out those brackets, those fractions that are equal to 1, because when you multiply by 1, you're not actually changing anything. And then once you multiply through by them and cancel out the units you don't want, you should hopefully be left with the units that you do want, and that's your solution. So we'll jump back to the lecture slides now. As you'll see in the slides, if you've looked at them online, they do have the full worked answers in there, which is just what I've done by hand. So I'll just skip over that one, but do feel free to read through that to reconfirm or reiterate that process. Sometimes you have a unit that looks a little more complicated, like centimeters squared or meters cubed. The best thing to do is to write them out without the exponents. So centimeters squared just means centimeters times centimeters. That's all squared means. It just means that thing times itself. So if you've got centimeters squared, write it out instead as centimeters times centimeters. And that way you can hopefully see very clearly that you're going to have to convert each of those centimeters into meters. You have to convert centimeter on the left into meters and the one on the right into meters. So you actually have to do the conversion twice. As an example, I won't do this one by hand. I've already done one. Hopefully you can follow this along quite clearly. 25 centimeters, convert it to meters cubed. If you like, you can pause the video now and actually have a go at these examples. Feel free to do that during all my lectures. Just pause them and have a go, and then see if you got it right once I continue on with the solution. So the first thing is to write it without the exponent. Centimeters cubed is equal to centimeters times centimeters times centimeters. We already know the fraction for meters to centimeters is 1 meter over 100 centimeters. That's just equal to 1, so we can multiply by that. But it's only going to change one of those units. So if we do 25 centimeters times centimeters times centimeters, and then we multiply by 1 meter over 100 centimeters, we've only cancelled out one of those centimeters, one of those units. And that means that what we've actually got is 0.25 centimeters times meters, which is not any useful kind of unit. So what we need to do is actually do that, multiply by that bracket 3 times, which is effectively dividing by 100 3 times, once for each dimension. Right? Because centimeters cubed is a volume, and a volume is 3 dimensions. It's got a length, a width, and a height, and you've got to change each dimension by 100. Right? Change it by a factor of 100. So if you take 25 centimeters cubed, you divide it by 100 3 times, once for each dimension, then you'll get 0.000025 meters cubed. And that is the correct answer for the volume of this box. There is a question on the problem sheet that asks you to do this, and it gets you to do it both ways, convert the original lengths into meters and then do the volume conversion and so on. So there is some practice. I do recommend having a look at that problem sheet. The trick, though, as I said, is to write out those units without the exponents. If you've got centimeters cubed, write it out as centimeters times centimeters times centimeters until you get the hang of it. Now, this isn't really relevant to unit conversions. It's just the first sort of relevant point for me to bring it up, and that is common sense in physics. One of the most common mistakes in physics is actually made after you've made a mistake, and that is the failure to think about your answer after you have it. If you do a calculation and you get a value and you don't stop and think, is this an appropriate value, then that is a mistake as well, and it's a mistake in picking up any mistakes you might have made. So if you do a unit conversion and it tells you that an adult human has a mass of 7.5 kilograms, hopefully you'll realize that's wrong. Right? Stopping for just a moment is all it takes to look at it and go, 7.5 kilos. Right, what was I actually looking at? Oh yeah, the mass of an adult human. Hold on, 7.5 kilograms seems a bit too small. About a factor of 10 out. It's more likely to be 75. So by stopping for just a moment, looking at your answer and thinking about what it was you were trying to calculate and whether it's a suitable common sense result will help you pick up a lot of mistakes. So that's something to get in the habit of as well. Sometimes, though, it's not so obvious. How do you use a common sense answer for something you're not familiar with? The example we had before of 53 kilometers per hour, it became what was it, 14.7 meters per second. How do we visualize 14.7 meters per second? It's pretty difficult to get an understanding. And if we had done that incorrectly, if we'd done it the other way around, if we had divided by 1,000 and multiplied by 3,600, then we might have got, for example, 3.6 meters per second. Right? If we make some mistakes and we get 3.6 meters per second instead of 14.7, how do we know that's correct? It's very difficult to know what 3.6 meters per second feels like compared to 53 kilometers per hour. You may find that if you visualize it, you can think about how long a second is and how far you're moving each second and realize you might expect to go a bit further than 3 meters. But if you can't, one other possibility is to work backwards. Take your answer and just spend a second calculating back to where you started from. If you have the answer that you're traveling 3.6 meters every second, then in a minute you've traveled that times 60, which is 216 meters. And then in an hour you've traveled that times another 60, which is 12,960 meters. So you've only traveled 13 kilometers in an hour. So if you said 3.6 meters per second, you are only at 13 kilometers an hour when we were supposed to be at 53 kilometers an hour. And it's just a little hint, or it's not a hint, it's a blatant statement that your answer was incorrect and you should go back and have another look. So common sense if you can. If you can't, think about just quickly calculating backwards to check your answer. The next part of this lesson is about scientific notation. To start with, though, we're going to talk about exponents a little bit more. I've already mentioned them when I was talking about centimeters squared and stuff. We're going to talk about them a little bit more. We already met the idea that an exponent just means something to the power of itself, to multiply by itself as many times as the power says. 2 to the power of 3 is 2 times itself 3 times. So 2 times 2 times 2. The reason we want to talk about exponents is for 10 to the power of something. So negative exponents, exactly the same idea, 2 to the power of negative 3, but instead you're dividing 1 by that number that many times. So 2 to the power of negative 3 means 1 divided by 2 3 times. So 1 over 2 times 2 times 2. So 2 to the power of negative 3 is the same as 1 over 2 to the power of positive 3. When we think about that in terms of 10, because our system, our number system, our counting system is in base 10, exponents of the number 10 are very neat and orderly. They're very patterned. 10 to the power of 1 is just 10 times nothing, right? Times itself 1 time, so just 10. 10 squared is 10 times 10, which is 100. 10 cubed, 10 times 10 times 10, 1,000, and so on. So you can just see it adds an extra 0 each time. 10, 100, 1,000, 10,000, and so on. 10 to the power of negative 1 is 1 over 10, which is 0.1. 10 to the power of negative 2, 1 over 100, which is 0.01, and so on. 10 to the negative 3, 1 over 1,000, 0.001. So exponents of 10 are this very easy to follow pattern. What they allow us to do is write numbers in a much more tidy and organized fashion where we're not likely to make many errors. So as an example, 245,000. If we write that as 24,500 times 10, so that's still the exact same number, we've just brought a factor of 10 out, we could write that as 24,500 times 10 to the power of 1. Alternatively, we could take 245,000 divided by 100, we get 2,450 times 100. But we already saw that 100 is equal to 10 to the power of 2. So we could write that as 2,450 times 10 to the power of 2, and so on. And so I won't read out the next couple of lines, but I'll go to the last one. 2.45 times 100,000 is our original value. We're looking for 245,000. So 2.45 times 100,000. But 100,000 is just 10 times itself 5 times. So we can write that as 2.45 times 10 to the power of 5. This practice of writing a number times 10 to the power of something is called scientific notation. And the reason it's called scientific notation is because it was literally developed to make big and small numbers easy to write out when you are doing scientific work. The reason that it's useful is, sorry, I'm a slide ahead of myself. I'll get to the reason in the next slide. Another way to think of the example is just how many decimal place moves you have to make. This is the way it's often taught. It's a practical way of thinking about it. It doesn't really help explain it, but it does help you think about it and just to double check your work. So if you've got 2.45 times 10 to the power of 5, that 5 means move your decimal place 5 points over. So your 2.45 becomes 245,000. But the reason it's useful is that we often deal with very large numbers. The mass of the sun, for example, is 1,989,000,000,000,000,000,000,000,000,000,000,000,000,000 kilograms. That is much easier to write as 1.989 times 10 to the 30 kilograms. It's a lot easier to write that. It also reduces the chance of any mistake. If I have to write out all those zeros every time and then type them into my calculator every time, or type them into my computer, or write them down again for the next line of the equation, I'm going to make mistakes. I'm just going to. It's impossible to do that repetitively without making any mistakes. But if you do 1.989 times 10 to the 30, it's a lot easier to get that correct every time. And so that's telling us that there are 30 integer places after the 1.989, so 1 and then 30 integer places. The other side of that is the negative exponents of 10, so 0.000245 we could write as 2.45 times 10 to the negative 4. And that is 2.45 divided by 10 4 times. Again, if you think about it as terms of the practical step you have to do to change the number, you just need to move that decimal place 4 places to the left. So 2.45 times 10 to the negative 4, move that decimal place 4 places to the left, tells you it is 0.000245. So that's negative exponents, and again, the exact same reason is there, that we can then write very small numbers. So the opposite is true going from a regular notation number to a scientific notation number. So those examples I gave before, I'm just going to go back for a moment. Here we said if you move the decimal place 5 spaces to the right, that'll convert it to regular notation. And for this one, 4 places to the left, convert it to regular notation. Often we want to go the other way. We've got a regular notation number, so that's something without scientific notation, and we want to convert it to scientific notation. It's just the opposite. How many times do you have to move the decimal place to get it to where you want it? The convention is after that first digit, so we want to move it up to between the 1 and the 2. We have to move it 5 spaces, so we have times 10 to the 5. Here we want to move it 5 spaces downwards, so it's times 10 to the negative 5. And again, I already mentioned this, but we get very small values as well. I'm not going to read this number out. The mass of a single electron is that many zeros followed by 910938356 kilograms. Again, you're going to make mistakes. You can't write that out over and over again without making any mistakes. So we use scientific notation, and that tells us it's 9.109 times 10 to the negative 31 kilograms. The negative 31, of course, telling us that the 9 is in the 31st decimal place. We divide by 10 31 times. So that's the use of scientific notation. Do get used to it. Do practice it. You will need to be able to use scientific notation. I already mentioned this as well. The convention is that we use the decimal place after 1 digit. That's where we want it. So we could take 245,000 and write it as 245 times 10 to the 3, but it is standard format to write 2.45 times 10 to the power of 5. So rather than leaving it as 245 times 10 to the power of 3. The reason for this is just so that we can easily compare numbers. There's an example right there with 1.38 times 10 to the 19 and 2.4865.656 times 10 to the 17. If you look at those two numbers, it might not be immediately clear which is the bigger number. If you've got a bit of practice or you're used to scientific notation, it does become pretty obvious. But if you use the convention, it's really clear because you have 1.38 times 10 to the 19 and 2.48 times 10 to the 19, or 49 if I'm rounding to 2 dp. We can easily see that the second number is larger. Right? Whereas if you look just at those first two numbers, that might not be as clear because one is times 10 to the 19 and one is times 10 to the 17. And so they might feel like they're different valued numbers, but in reality, the second one is slightly larger. Going from scientific notation, we introduce prefixes. So we've talked about the idea of writing a number as times 10 to the power of something. Sometimes writing even times 10 to the power of something can get a bit cumbersome. If you're writing times 10 to the power of 9 every time you write a number out, that can get a bit tiring as well, whereas you could instead just put a big capital G in front of your unit. So if you had meters, and then all of a sudden you were in times 10 to the 9 meters, you could just write gigameters, GM. So these are some standard prefixes. There are more, do feel free to look them up. Generally, when you encounter a prefix, go and check it. unless you're really, really confident. Most people are pretty happy with milli being 1,000th, 10 to the negative 3, or kilo being times 1,000, 10 to the positive 3. But the other ones, most people generally will need to go and check. I do want to draw your attention to micro. That's the prefix, that little curvy U shape. It's a Greek letter. And I don't just want to draw your attention to it because it's a Greek letter. I want to draw your attention to it because it is one of the most commonly misinterpreted prefixes. It is very common to get that one wrong. So do try and pay attention to micro whenever it occurs. It is times 10 to the negative 6 for micro. Converting from prefixes is very easy. We just take the prefix letter and replace it with the scientific notation for that value. So centimeters, we saw centi was 10 to the negative 2, so we replace C with times 10 to the negative 2. Micro, we replace it with times 10 to the negative 6, and giga, G, we replace with times 10 to the positive 9. That's all you have to do to convert from. I don't have a slide on converting to, but it's just the other way. Once you've got your value in this format with a scientific notation that is equal to one of these prefix values, then you can just swap that scientific notation. So it'll just be going the other way. If you had something times 10 to the negative 6, you can write something with a micro after it instead. Now, the last part of this lesson is also one of the trickier ones, but we will go over this in the lab. If you get given a value with an uncertainty, that's this little plus or minus figure at the end of it, what it's telling you is that the person who took that measurement or who found that result is only confident that the result is within that range of that central value. So there's a couple of terms that I need to explain there. Firstly, central value. So the result itself, in this case 5.35, that is your central value. And the plus or minus is just saying either above or below that central value. And then the next number, the 0.07, is how far above or below they think the real value could be. And we don't know what the real value is, that's the point, but we are confident it's somewhere in that range. I'm just going to jump back to the document camera. I just have to get a new sheet of paper. We'll jump back to the document camera for a moment, and I'll just reiterate this. If we've got the value of 5.35 plus or minus 0.07 meters. What that means is that we think 5.35 meters, that's our central value, but it could be up to 0.07 higher, right? So it could be, we'll go 1, 2, 3, 4, 5, 6, 7, could be all the way up to here, right? So that's 0.07 meters. It could be all the way up to here. Hopefully you're all familiar with number lines because that's all I'm doing. 1, 2, 3, 4, 5, 6, 7. Or it could be all the way down to here. So the central value was 5.35, but the plus or minus 0.7 is actually telling us that it could be anywhere in this whole range. This whole range is actually your result. That's what an uncertainty does. It says, that's your central value. This is how far above or below it might actually be, but we're pretty confident that it's somewhere in this range. That is the point of an uncertainty. And as I said, in the labs, we will deal with uncertainties. You'll get a chance to work through a lot of them. So the key message, thing I'm going to say again, is that the result is a range. If you ever have a value with an uncertainty, your value is not just a number, it is a range. It is anywhere in that region. In this case, 5.28, that's 5.35 minus 0.07, up to 5.42, which is 5.35 plus 0.07. So it's anywhere in that range. So please remember, a value with an uncertainty is a range. When you take a single measurement, you have an uncertainty. Taking a measurement will introduce uncertainty. It is impossible to get a measurement with zero uncertainty. It is just not possible. You can get a count with zero uncertainty. As I said before, I've got 2 pens. Right? There's 2. There's no units for that. There's also no uncertainty because I know there are 2. Right? There's no uncertainty. I'm not saying, well, there's between 1 and 3. I know there are exactly 2. So generally, though, any measurement you take will have an uncertainty. I've got an example here of a very large paperclip with a ruler. All you do is you read off the ruler what your measurement is. Yeah, that's something you're all used to doing. That tells you that central value, that central result. So if we just read off this, it looks like it's about 8.1 centimeters or 81 millimeters. 8.1 centimeters. But when we took that reading, we just said, well, the 8.1 is the closest line to the end of the paperclip. It might not have lined up exactly, but it was the closest one, so we're just going to go with that. That might make you think that you could be up to 0.5 millimeter bigger or smaller, and you might think your uncertainty should be 0.5 millimeter. But remember that you also chose where to line up the start of the paperclip with the start of the ruler. And that introduces another 0.5 millimeter of uncertainty. So because you've got a 0.5 millimeter at the end and a 0.5 millimeter at the other end, that means you've got a total uncertainty of 1 millimeter. And for that reason, we generally will always take the entire least count as our uncertainty for measurements. So if you have a measurement device like a ruler, you find the least count, which is the smallest division on that scale, and you use that as your uncertainty. I will talk more about this in the labs. As I said, we'll work through a few uncertainty measurements and so on. The other thing I just want to point out is that because of this, we never interpolate our results. If it looks like it's halfway between 8 and 8.1, we don't say it's 8.05, we just take the nearest line, right? Always take the nearest value and then use the least count as your uncertainty. Every time you make a measurement, things can change slightly, right? Whether it's the alignment, whether it's the position of you, whether it's the object itself, things can change slightly. That is called random error. Random error is the idea that you could repeat a measurement and get a different value every time. For example, you might have a little electronic balance, you've got a little ball that you're trying to measure, or some object, and you put it on the scale and it tells you 15.26 grams. But then you take it off, you reset the scale, you put it back on, and it says now it's 15.31 grams. Then you do it again and it says it's 15.29 grams. Those variations are random errors. Random errors are just going to be just random changes in the result due to things that you can't control, things beyond your control for the setup. That is why we will often repeat measurements. Repeating measurements will average out those random errors. Because if a random error is just as likely to make your value bigger as it is to make it smaller, then if you do it a whole bunch of times, on average, those random errors will end up being 0. There is another type of error though, and that is the systematic error. The systematic error is harder to detect because it is part of the system itself. The system in this case is the whole setup you're using to take the measurement. So it might be the ruler and the object and you reading the ruler. The systematic error might be, for example, you're using I think there's an example given on this slide, a tape measure, and the tape measure has been stretched from overuse. Every time you use that tape measure, excuse me, it might give you the exact same result, but that result is wrong because the tape measure is wrong. And that is called a systematic error. It's a problem with your system. And if you just keep taking that measurement with the tape measure, you'll be really confident in your result, but you shouldn't be because the tape measure itself was wrong. There is no way to know whether there's a systematic error unless you go and take the same measurement with a different system. So if you measure something with the tape measure, and then you go and you measure the same thing but with a different ruler, and then go and measure it with a different ruler, and so on, that can help detect systematic errors. But as long as you keep using the same system, the same measuring device, and the same object, and the same person reading it over and over again, you are always using the same system. You are never going to detect any systematic errors. When we're in a lab setting, we sometimes need to estimate uncertainties. I said that we can use the least count of the device in some cases, and that is often true. But sometimes you're recording something and you actually want to estimate the uncertainty to be bigger than the least count. For example, you're timing a pendulum, right? Pendulum, we all know a pendulum, just a thing swinging back and forwards, and you're timing how long it takes to do one swing. The stopwatch you're using goes down to 1/100th of a second. The question is your least count likely to be your uncertainty in this case? I don't think I've got an answer for this one, but I will answer it now. I also encourage you all to talk about it in the stream forums if you are unsure or you want to just chat about it, I would hope you agree it shouldn't be, right? It shouldn't be the least count, because that least count on your stopwatch is not the thing which is restricting how accurate your result is. Right? You are the thing that's restricting how accurate it is. You are watching the pendulum. You are choosing when to start and stop the stopwatch. Do you think that you can start and stop the stopwatch within 1/100th of a second of the pendulum actually being at its position of maximum displacement? That's the end of its swing. Do you think that you can time the end of its swing to within 1/100th of a second? Because I certainly don't think I can. In which case you want to estimate your uncertainty and you make it bigger. In such a case, you might often go and repeat the measurement, see how spread out all your results are, use that to get an idea of your uncertainty. But normally you would definitely estimate it to be bigger than 1/100th of a second. Once we take our measurements, we have values with uncertainties. We sometimes want to do a calculation based on it. Remember that we often do indirect measurements. That means we've taken measurements, we need to do a calculation to get the value we're actually concerned with. In this case, we're going to talk about that giant paperclip we had. Let's say we had 2 identical giant paperclips and we want to know how long they would be placed end to end. Our equation is 8.1 plus or minus 0.1, because that was the length of one paperclip, plus the same thing again, plus 8.1 plus or minus 0.1. To solve this, we need to use something called brute force. And brute force is just a method for doing a calculation with uncertainties. And essentially, you have to do the calculation twice. I know you all love maths and calculations, so I'm sure that's not a problem. You have to do it twice. You do it once using just those central values, or middle values, as I've called them here, just those central values, and you add them together. So forget the uncertainties for a moment, do your calculation without the uncertainties, and that'll give you your middle value, your central value for the result. In this case, 8.1 plus 8.1, which is 16.2 centimeters. And that makes perfect sense. If the central value of your initial measurement was 8.1 and you double it, you'd expect the central to be 16.2. The next step of brute force is just to think about how big you can possibly make your answer. Remember that we said it was 8.1, but it could be 0.1 bigger or smaller. So it could actually be as big as 8.2. And then the second paperclip could also be as big as 8.2. And if they were both right at that biggest end of that range, then our result would be 16.4 centimeters. And that's our largest possible value. And that's all the second step is. It's to repeat the calculation, but making everything as big as you can. Sorry, I should say making the result as big as you can. As you'll see, sometimes we need to make values smaller. But in this case, adding them together, make both the values bigger, will make our result bigger. And that tells us the largest possible value. And if you remember the number line with our range on it, our central value, and our largest and our smallest, the largest possible value is telling us how big that range is from the central value. So that means that once you know the central and the largest, the difference between them is your uncertainty. So the difference here, 16.2 up to 16.4, is 0.2 of a centimeter. So our result would be central plus or minus 0.2, which is 16.2 plus or minus 0.2. Again, you will get to practice this in the labs. There are also a few problems on the problem sheet, not too many, because the focus is going to be in the labs for these sorts of calculations. Let's suppose we've got something a bit harder. Let's say we're doing an area, which is a length times a height. So we're not just adding anymore. Length times a height, it's actually the exact same process. We ignore the uncertainties to get our central result. So area 3.4 times 4.6, that's ignoring our uncertainties, tells us our central value for our result is 15.64. We then find the largest possible area. So the largest possible area would be when both the length and the height were right at the top ends of their ranges. And that gives us 16.8 as our largest possible area. The difference then tells us the uncertainty, which in this case is 1.16. So that means that we have 15.64 plus or minus 1.16. I have ignored units. Normally you wouldn't ignore units, you'd have units right through, but I have not put them in there just because it doesn't matter whether they're meters or centimeters or millimeters. The process is always the same. Find the middle value, find the largest value, and then the difference is your uncertainty. So that's straightforward enough. But what about if we're doing a subtraction instead? If we make our inputs bigger, then that would make our results smaller, because if you take away a bigger number, you're left with a smaller result. We always want to make the result as big as we can. So to make the result as big as we can means that if you add something or you multiply something, you make them bigger. But if you subtract something or if you divide by something, you want to make them smaller, because that will make your result bigger. So in this case, you've got a mass which is it's taken from a lab type example where you've got a mass of water which is equal to a total mass minus a beaker mass. And there's uncertainties on both of those inputs. The extra words are just sort of to muddy things up, and hopefully you can still follow it. So try and follow along just with all of those calculations in there and the extra words that aren't really necessary, not for your purposes right now. So exactly the same process. Find the central value, which is ignore uncertainties, do the calculation, then find the largest value. As I said, you have to make the thing that you're subtracting smaller in order to get a larger possible result. You can see there I did it once without making it smaller. I made the subtracted number bigger, and that gave us a smaller result. But if you make the subtracted number smaller, you get a larger result, and that will then tell you the uncertainty. Same with division. As I said, if you're doing a division, make the thing on the bottom smaller, because if you divide by a smaller number, you get a bigger result, right? I always talk about cake for this one. If you've got a cake and you're dividing it by fewer people, you each get more cake, right? Here, you want to make the result as big as you can. You want more cake, so therefore you divide by fewer people. You divide by a smaller number. The last part of this lesson is going to talk about how we present our results. So significant figures is how many meaningful digits are in a number. The number 1.2 has two significant figures because the 1 and the 2 both mean something. But the number 0.2 only has one significant figure because the 0 doesn't actually mean anything in terms of the value. It doesn't change the value of that 2. It helps us know where the 2 is. We always write 0.2, not just 0.2, because otherwise it might look like you're just starting a new sentence with the number 2. So 0.2, 0 is not significant, the 2 is. 2.0 though has two significant figures. If you write 2.0, the only reason you would write 0.0 is if you know that that number after the decimal place is a 0. So that's telling us that that 0 is significant. Lastly, the number 20, that's actually ambiguous. We don't know if the 0 is definitely a 0, if the person who wrote it knows that it was a 2 and then a 0, or they might just know it's a 2, but they need the 0 so that you know the 2 is in the tens place. So that is actually ambiguous. So generally, if you've got an ambiguous number, you should write how many significant figures it is in brackets afterwards, 20 as 2SF or 20 as 1SF. So there are, again, a few questions in the problem sheet about significant figures. You do want to be confident in those. I think I've got a significant figure cheat sheet as well that I'll just chuck up on stream as a bonus resource for this lesson. So do check that out as well if you're not sure. The reason we want to talk about significant figures is for expressing experimental results. We always express uncertainties with only one significant figure. This is not a worldwide true statement. This is just for this course and for physics at Massey University. We do uncertainties to 1SF, one non-zero digit. So suppose we have a measurement of 1.5892 units and our uncertainty is 0.0356 units. We round our uncertainty to one significant figure, which is 0.04 units. Right? That's just basic rounding. 0.0356 rounds to 0.04. So as I said, the rule is one non-zero digit. So you can write as many zeros as you need to put it in the right place. So we have 0.0 so that the 4 is in the right position. But as soon as you write 4, that's our one non-zero digit taken up. We can't write any more. We can't write anything else after the 4. Then the rule for us, again, this is for physics here at Massey, is that once we have that place value for our uncertainty, we round the result, that central value, to the same place value. So in this case, the 0.04, that 4 is in the second decimal place, so you would round our result from 1.5892 up to 1.59. So we would present our result as 1.59 plus or minus 0.04 units. That's our convention for rounding for this course. So please do recall that again. This applies to the lab work. Occasionally I'll throw it into an assignment or a test, but generally the lab work is where you'll see this mostly. Sometimes the uncertainty rounding can be a little bit confusing, mostly when we have, for example, a very large number. 232 is our uncertainty. That seems like a big uncertainty, but the value itself is 100,000. So it's still a fairly small uncertainty. That 232 can still only be one significant figure. So it becomes 200. That 2 uses up our one non-zero digit. So all we can do is add some zeros to put it in the right place. So that is our uncertainty to 1SF would be 200. We then have to round the value, the central result, to the same place value. Since our uncertainty is rounded to the nearest whole hundred, we have to then round our value to the nearest whole hundred, and 104,590 becomes 104,600 to the nearest whole hundred. So we would present our result as 104,600 plus or minus 200. Uncertainties can also be expressed with scientific notation, the same exact rules, one significant figure for your uncertainty, and then match the place value for your result. The issue here is that the place value can be a little bit confusing. You have to remember what the scientific notation means. In this example, 1.256 times 10 to the negative 7 tells us that that 1 is actually in the 7th decimal place. So when we round that to 1 times 10 to the negative 7, that 1 is in the 7th decimal place, not in the whole ones number, it's in the 7th decimal place. That means our actual result that we then need to round, 4.532 times 10 to the negative 5, remember that that negative 5 is telling us the 4 is in the 5th decimal place. So we don't want to round there because that's only 5 decimal places. The 5 is in the 6th decimal place, and that 3 would then be in the 7th decimal place. So that would be where we'd want to round to, 4.53 times 10 to the negative 5 would be the correct rounding. That can be a little bit confusing though until you're a bit more confident with scientific notation. So one thing that I do recommend you try doing if you're not confident with rounding scientific notation results is to convert them both to the same exponent. So rather than having 1.256 times 10 to the negative 7 as your uncertainty, change the scientific notation. Move that decimal place 2 places to the left, and that will change your scientific notation to times 10 to the negative 5, which now matches your result, your central value. And you can then put the scientific notation outside brackets. You can factor it out. Hopefully you're familiar with maths and factorization. If you've got times 10 to the negative 5 on both parts of that, you can factor it out, and you get 4.532 plus or minus 0.01256, all times 10 to the negative 5. And that means you can then round as we normally would without the scientific notation, and that times 10 to the negative 5 just sits on the outside of that bracket. So that's it's uncertainties in scientific notation. The last thing I want to do is define a couple of terms just quickly. They relate to uncertainty, that's why they're included in this uncertainty section. When we talk about accuracy, we mean whether or not the value agrees with the actual value. Right? So if your result agrees with the actual value, it is accurate. Sometimes that can be hard to determine. Sometimes you don't know the actual value, so you don't know if you're accurate or not. But accuracy is just whether or not it is accurate. Precision, in everyday language, again, accuracy, precision, often used in the same sort of way. There is a slight distinction sometimes with the way some people use them, but in physics or in science in general, there is a very clear distinction. Accuracy, as I just said, is the accurate, whether or not your result is accurate. Precision refers to how large your uncertainty is in relation to the result. The smaller the uncertainty, the more precise your result. So an example that I often give here, I can't recall, no, I haven't included it in a slide. An example I often give here is, let's say I'm measuring a bench. I might actually, I'll go over to the document camera and just draw it for you. Let's say I'm measuring a bench. So here's my bench, and let's say that it is actually 2.5 meters long. So that's the actual value. Now, as I said, sometimes you don't know the actual value, but we're going to pretend we do for now. If I tell you that this desk is 10 meters plus or minus 8 meters, then that means I'm saying it's somewhere between 2 meters and 18 meters. So that is accurate It is accurate because it agrees with the actual value. 2.5 is inside my range. So it is accurate, right? But it is not precise. It's not precise because my uncertainty is almost as big as my value. Right? 8 is almost as big as 10. So accurate but not precise. On the other hand, if I said that it was 5.124 plus or minus 0.00000001 meters, this uncertainty is tiny compared to my value. So that is very precise, but it is not accurate. So you can easily be one but not the other. Our goal, of course, is to try and remain accurate while increasing our precision to a reasonable level. So your result may end up being, if you use a tape measure to measure it, you may end up saying that it is 2.51 plus or minus 0.02 meters. That is accurate because you're saying it's somewhere between 2.49 and 2.53, and that agrees with the actual value, so it's accurate. And it's also reasonably precise. 2 centimeters out of 250 centimeters is a pretty good uncertainty. So that is generally our goal, to be accurate and reasonably precise. And as usual, there is one last slide, which is just the review. It lists everything that we've gone through quite a lot in this lesson. As I said, it was broken up into parts. This hopefully, though, has set you on the path for your experimental physics journey, which will, as I said, be a sort of separate journey. You do have to get through certain lessons in order to approach each of the experiments, but we will deal with them separately. So go over to the physics labs page, and from there you can explore the first lab, Lab 0, which is the introductory one, and then move on to the other labs as you complete the relevant lessons.